So here is another example where we try to do the time domain analysis of this circuit. So note that the position of resistor and the capacitor is swapped now. In the earlier version of the circuit, we had this voltage source and we had this resistor and capacitors arranged like this. So C was right here, R was, and the values were same. So the frequency of this circuit is given as 2 pi RC, that is the cutoff frequency. And for this circuit also, the cutoff frequency FC is given by 1 over 2 pi RC. So now the point is, let's understand how this circuit will behave. So to do that, we actually have to design, let's say we design this circuit for a cutoff frequency of 1 kilohertz. So again, we choose the value of C to be of 0.1 microfarad and we calculate the value of R for a given value of C and F. So that comes out to be 1.59 kilo ohm. So here is that value, and here is the value of capacitance. Now for the voltage source, we have to run the sinusoidal analysis. So we want to apply a sine wave signal to this RC circuit, and we want to understand from frequencies of 0 to cutoff frequency how the circuit will behave, and from cutoff frequency to the frequency which is very high than the cutoff frequency, ideally it is infinity. So from FC to a very high frequency than FC, how the circuit behaves. So two conditions we have to understand. So we'll see now how these time domain analysis will do. So let's try to run the simulations. So before that, we just need to understand one thing, that we can use this example to understand the analysis. Right click the voltage source, and here we see that we have selected this sinusoidal voltage source right here, and then all the parameters are given. So you see DC offset voltage is set to 0 volt, amplitude is set to 100 millivolt, peak frequency is set to be 5000 hertz. So cutoff frequency of this circuit is 1 kilohertz, which is our design frequency, and we have set the frequency to be 5000 hertz or 5 kilohertz. So it's 5 times larger than the design frequency. So we'll see if the input signal of the frequency 5 kilohertz will get passed through this network and appears at the output. And with this, we click here, run the transient analysis. So we see here that we have transient analysis. We are stop time, we have chosen it to be, let's say 10 milliseconds, or let's say, yeah, 10 milliseconds, and time to start saving data is 0 seconds. We can also choose maximum time steps if we require, otherwise we leave the field blank. Okay, and we click OK, and we will run the analysis to see how the results look. So first we just click the node A, which is this net, to see our input waveform. So here we see that the sinusoidal input varying from 0 to 100 millivolt peak, and then output, we come here and we click the node out, and we see here, if we zoom in this portion, we see that we have this output of the circuit is following the input. It means input waveform of 5 kilohertz signal frequency appears at the output. So it basically filters this kind of signal. So the cutoff frequency is 1 kilohertz, which is less than the applied signal frequency. That's why the circuit will pass this signal frequency. If we right click the voltage source again, and this time we choose the frequency to be, let's say, 3000 hertz, and we click run again. So again you see that you have this signal. So what I do on the waveform window, I left click the mouse and select this portion and zoom in. So I see now the output is still equal to input in amplitude and the frequency, and approximately the input signal of 3 kilohertz passes through the network of RC and appears as the output. Because the design frequency is 1 kilohertz, so it is successfully filtering out all these signals which are greater than 1 kilohertz. What about we choose 1 kilohertz or 1000 hertz? So now I input this signal, and now let us see the response. So we'll simulate. Now you see the input is 100 millivolt peak and the output is about 70 millivolt peak. So it is 0. So it is 30 millivolt less than the original value. So if we say the 1 volt is the input, so the 0.707 will be the output signal magnitude, and the frequency is also. So from this we'll say that this is at the borderline. We have, this is the limit where we can actually uh, pass the signal of a frequency of 1 kilohertz, but little bit attenuated output is there. What if we again reduce the frequency? Let's say I have about 500 hertz and the design frequency of the network is 1 kilohertz. So we'll see that the output signal should significantly drop now. So we'll run, and as expected we see that the signal is keep dropping. The green is the input and the blue is the output. Again we come back to the voltage source, right click it, and if I select about only 100 hertz signal frequency, I run the analysis, and just to see that the output is significantly dropped. So to have more cycles, what I'll right click on the transient analysis. So I am here and I'll increase the stop time, let's say about 100 millisecond, because we have decreased the frequency, the time, stop time should be increased. So we'll click OK and again run the analysis. So now we have input in green and the blue is the output, but it is much attenuated than the input. So whatever we applied as an input, that appears at the output, but in a much attenuated form. So we'll say that this circuit is basically acting as a high pass filter. So it is passing all the frequencies greater than its design frequency, that is 1 kilohertz, but it is attenuating significantly signals of frequencies less than the design frequency, which is 1 kilohertz. So any signal less than 1 kilohertz frequency is getting attenuated, and all signals greater than 1 kilohertz design frequency is getting passed. So that's how this circuit works as a high pass filter, and we saw how to perform a time response or time domain analysis of this particular signal. And based on the formula of fc equal to 1 over 2 pi rc, we can design the circuit and simulate for a given design frequency. So next module we'll see how to obtain the AC response or frequency response of the same network. So which is nothing but a body plot.